Shannon said we're going to talk about soil test reports. What I wanted to do is go over how to interpret what each sort of value in your soil test report means and what that means for management. Um, so let me go through. If you guys have questions as we go along, you can just, I guess, pop them in the chat and I'll try to keep my eye on that and answer, and then we'll hopefully have some time at the end to go through. So what is the objectives for today? Well, I want to cover the importance of soil testing, and really, if you don't get anything out of this session, is if you're going to do anything with soils for management, really your soil test is going to be the most important part of that, the most important step. It's the first step. You don't want to do anything to your soil before you test it. Now I'm going to take a sample report and go through what each section means, and then I will talk a little bit about management decisions based off of what those numbers mean in your report. So why do we do soil testing? A lot of you already know this, but just to reiterate, it's going to help you make better management decisions. It might help you decide what you're going to plant and where. It's really going to help determine your inputs, how much fertilizer you need, how much lime you might need. Altogether, it's to drive improved profits, all right? And then the second part to this is to sort of track your soil properties over time. That could be nice to see a general trend as to what your soils are doing and how your management is affecting different soil parameters. So this is just an example of two different pastures as a visual. So there's obviously a lot more going on here than just soil testing and soil management, but I could tell you that the pasture on the right, which looks phenomenal, they've probably done a lot of homework into managing their soil and doing proper soil testing and really dialing in what that soil needs for that pasture, versus the one on the left where we have a lot of weed encroachment, a lot of undesirable forages, and I would venture to say that that's just sort of like an unmanaged type pasture, and they're not really putting effort into managing that soil. So if you're going to have crops that look like the one on the right, you're going to have soil testing worked into your plan. So what I'm going to do is go through a sample soil analysis report. This one is just an example that I'm using for this. This is from Waypoint. Waypoint's a popular lab in our region. I'm not endorsing them in any way. They have some good examples up on their website, so I just pulled them off. So what I'm going to do is sort of go through each section. I'm going to talk about them in sort of the order that I look at a soils report. And the first thing that my eye is always drawn to in a soil test report is going to be pH. So in this Waypoint report, it's sort of over on the right-hand side under the pH column. And my eye always goes there first because really that's going to be the most important chemical property of your soil is your pH. So I want to know where the soil pH range is. So what is soil pH? Well, simply put, soil pH is just the measure of the acidity or alkalinity of your soil. Specifically, what we're measuring is the concentration of hydrogen ions in your soil solution, so the soil water, all right? In a lot of reports, you might see two values represented under pH. One is the soil pH, and then you might see another one called buffer pH or buffer index. So your soil pH is the actual pH of your soil. All right, that's the number. So in that first sample, this soil is at 6.5. The buffer index is the measure of your soil's reserve acidity, and I'll talk about that here. But basically, what that means is if that number is close to your soil pH number, that means that your soil is highly buffered. It means that you have a lot of reserve hydrogen ions in your soil, that when you lime your soil to bring your pH back up, your soil is going to actually release more hydrogen back into soil solution that combats that liming action. So those numbers, if they're closer to your pH number, then that means your soil is more buffered. Basically what this means is it affects how much lime you have to apply to your field or to your soil in order to bring your pH up. So if your pH is low, that means it's acidic, and if it's outside of the ideal range for plant growth, we're going to have to lime our field to bring it back up to a more neutral number. That reserve acidity will affect how much lime you actually have to apply. So you can think about it in sort of a visual sense here. Really, you have two pools of hydrogen in your soil. You have the one on the right-hand side, which is your soil solution. That's your actual soil pH, right? That's this pool on the right. And then you have this other pool pictured on the left, which is reserve hydrogen. When you measure soil pH, you're not measuring that reserve. But what happens is when you add liming material to bring out to raise your pH, what that does is it binds to some of the hydrogen that's in your soil solution and it pulls it out of solution. So there's less hydrogen ions in that soil water, which in turn raises your soil pH. Now, if you remember from chemistry class, and you understand that energy moves from a concentrated state to a less concentrated state. So what happens is all this reserve hydrogen wants to move back into this lower concentration area. So once we pull some of this hydrogen out of solution, what's in reserve locked in your soil is going to be released into the soil water, and that's going to act to bring your pH back down. All right, so that's the difference between reserve acidity or buffer pH and actual soil pH. Now, some soils have really big reserve pools, like this one pictured here on the left, which will require a lot more lime to raise the pH versus something that has a smaller pool, which would require less lime to bring up your pH. Soils that are less buffered, like this one, for example, are really easy to over lime. So you really have to pay attention to how much lime is recommended and not to go over that, because you could bring your pH up too high too quickly, and that would not be good. It would be out of the sufficient range. So again, soil pH is the actual pH of your soil. This buffer index or buffer pH is the measure of that reserve acidity. Again, you don't really need to do anything with that number, because that buffer number is going to be used by the lab to calculate your liming rate. But just for your information, that's what those two numbers mean. You'll notice that some of these, for two of these soil samples, the buffer pH number is actually not even there. And the reason that is because the lab doesn't even calculate it if your soil pH is in the ideal range, which is generally between 6 and 7. So they don't even bother to calculate that number because no lime is required anyway. So if we look at these two soil samples that I circled here, remember I said if the buffer index number is closer to the actual soil pH number, that means it's more buffered than if there's a greater difference. So in this instance, the soil at the bottom is going to be a little bit more buffered than the soil at the top. So again, there's not a huge difference between these two examples, but because the 6.85 is closer to 5.9 than 6.83 is to 5.7, that means that this one down here is going to be the more buffered one, which in terms mean that this one is going to require more lime to bring it up to, say, pH of 6.5. So I just filled in some sort of made up numbers here, and these numbers are just to visualize this as to, say you have two soil samples that you submitted to the lab, and they're both at pH 5.6. However, you look at the recommendations and you notice that one soil is requiring or recommended to have, say, 1 ton to the acre of lime, and the other is at 1.5 tons per acre to lime. And say you're growing the same crop, so you might wonder why one soil is requiring half a ton more lime than the other to bring it up to the same pH. Well, it's because this soil here, the second one, is more buffered than the first soil. So this soil here has more reserve acidity that will neutralize that liming material that you add. So that means you have to add more liming material to bring it back up to that desired pH level. So hopefully that makes sense, okay? If you understand that part, then the rest of this is going to be a breeze, okay? Okay, I see in the chat that they got it, good. All right, so I would say that's kind of the more complicated thing to wrap your head around in a soils report. The rest of it's a little bit more straightforward, I think. So when I look at a soil test report, I'm always interested at looking at soil organic matter, and related to that is going to be CEC, which is cation exchange capacity. So in the waypoint report, you have organic matter all the way to the left, and you have CEC on the right, and I'll explain what they are. So CEC stands for cation exchange capacity, and that's the ability of your soil to retain positively charged ions. And if you remember back from chemistry, positively charged ions are called cations. A lot of your soil's ability to hold on to cations come from soil organic matter, and it also comes from clays. This is because there's a lot of negative charges on organic matter and clays, and those dangling negative charges are basically parking spots for these positive ions. The reason that that's important is because a lot of our nutrient inputs, fertilizers, whether they be organic or synthetic, a lot of them are positively charged ions, or at some point in their cycle they're positively charged. The reason that's important is because we can hold on to those nutrients, and we can hold on to them until the plant needs them, and then the plant will take them up. So that's why cation exchange capacity is desirable, and it's important in your soil. If you have a higher cation exchange capacity, you have more parking spaces for nutrients. That's basically what it comes down to. And again, a lot of that comes from your soil organic matter and also your clay content in your soil. So soil organic matter is just simply, it's the organic component of your soil. It's expressed as a percentage of weight of your soil. All right, and soil organic matter, while it only makes up a very small percentage of your soil, for us, if you're in the 2 to 4% range, you're doing good with soil organic matter. But that 2 and 3 and 4% has a very huge impact on your soil chemical and physical properties. It's going to affect how much water your soil can hold. It's going to affect how much water can infiltrate your soil. It's going to affect your cation exchange capacity. It's going to affect your soil structure. It's going to reduce compaction. So all these are really desirable characteristics made up by soil organic matter. Now I want to go back to cation exchange capacity for a second. Cation exchange capacity is expressed in what we call milliequivalents per 100 grams of soil. That's what this means. Basically, the higher the number, it means you have more cation exchange capacity. So that's good. So we can see in the soils listed here, this first one has 5.4 milliequivalents per 100 grams. That's the highest one on this list. That's kind of normal for our types of soils. You might see them range from, say, they might range from 3 or so up to, it depends how much organic matter you have, but generally 3 to 5 or 3 to 7 is going to be kind of normal for our soils. But the more organic matter you have in soils, you'll typically get higher CECs. If you compare our type of soil to like soils that have a lot of organic matter just naturally from the parent material, like for example, if you go out into the prairie states, the Corn Belt, where they have really thick, really dark, high organic matter soils, their cation exchange capacities are up in like the 20s. It's a lot higher. Your CEC can't really be too high. Again, you're able to park more nutrients in those spots with higher CECs. There's a couple of rough estimations that you can do as a calculation. So if you take your CEC and you multiply it by 10, so just move that decimal spot over to the right, roughly that's about the amount of nitrogen that your soil can hold at a given time. So for example, if you go to, say, the second one, 4.9, that soil can hold about 50 pounds of nitrogen per acre. So that's why here in Maryland and a lot of other states in this region that have similar soil types, it's recommended to split apply your nitrogen because our soils can only hold on to so much at one time. If I apply, say I apply 200 pounds of nitrogen to this soil that only had a cation exchange capacity of 4.9, if I put all 200 units of that up front, I can almost guarantee that, 100 to 150 pounds of it is just going to be lost because there's just not spaces for it in our soil. So I like looking at CEC to help judge my nutrient application splits, really for nitrogen. I think it's really helpful to know. So in these examples here, you wouldn't want to apply more than, say, 50 or 60 pounds of nitrogen at one time to these soils, just because it's probably not going to be held there. The other thing that you can do related to nitrogen is for every 1% of your organic matter, roughly 10 to 60 pounds of nitrogen is going to be mineralized or released out of that organic matter per year to your crop. So if we have, and that's going to be heavily dependent on the type of growing season we have. So if we have sort of an ideal growing season where we get decent moisture but not too wet, you're going to be closer to that 60 pound range. If we have a really dry year, for example, or a really wet year, or a really cold year, then you're going to be closer to that 10 pound mark. The other thing that I should mention about soil organic matter is that the calculation that the lab uses to come up with your soil organic matter, different labs use different methods, all right? Most of the common ones that most of the labs use around here is the loss on ignition method, all right? But there is others, the Wakely-Black method, which is more of a chemical determination of soil organic matter. And there's also a different method called combustion, which is different than loss on ignition. The point to be made here is that different labs use different calculations. So that's why we sort of recommend that you pick a lab and just sort of stick with that lab, because there could be differences in how they're calculating your soil organic matter. So you might, if you switch a lab and you all of a sudden notice a really big discrepancy in how much organic matter you have in your soils, it would be a good idea to probably go back and see how they're calculating organic matter, because I would bet that they're using a different method than what you had previously been using. All right, so next is what we call base saturation. Now this is somewhat related to cation exchange capacity. All right, so on the Waypoint lab, we see a section for base saturation in the lower left. And what base saturation is the percentage of your cation exchange sites, so those parking spaces, that are occupied by what we call basic cations. So the basic cations that are occupying those spaces that are measured are potassium, magnesium, calcium, sodium, and hydrogen. All right, so they're always going to sum to 100%. So most labs will report the individual numbers. I've seen some labs, they will leave out hydrogen sometimes, but you can easily calculate that, because if you add up the other 4 and subtract that from 100, you can get your hydrogen. So when you look at these percentages, I don't even have to look at the soil pH number to tell you right off the bat that this third one, for example, is probably going to have the most acidic soil. It's probably going to have the lowest pH, because look at how much hydrogen is on those cation exchange sites. And in this instance, it is the most acidic soil. So you don't even have to look at soil pH. If you look at your base saturation with hydrogen, you can already tell which one is going to be the most acidic. Now, these are just some rough, ideal, quote unquote, base saturation numbers for crop production that you could kind of strive to maintain. For potassium, we want about 3 to 5%. Magnesium, somewhere 10 to 20. Calcium is the one that you want the most of on your exchange sites. That's going to be 50 to 75%. Sodium, which is salt. Salt is not good to have at very high concentrations for plant growth, so we want less than 2%. And ideally, you should be less than 10% for hydrogen. Now, you could influence these numbers by different management practices. So, for example, when you lime your soil, you're going to bring down your percentage base saturation of hydrogen, all right? Likewise, if you lime with, say, calcitic limestone, calcium carbonate, you're going to bump up the percentage of calcium on your exchange sites. If you lime with magnesium carbonate, you're going to bump up your magnesium base saturation. And if you fertilize with potash or potassium-based fertilizers, you're going to bump up your potassium base saturation. All right. So I just kind of reference this table sometimes. You know, when I'm looking at soils, those are sort of some base numbers to kind of strive for. The reason we want to be in these ranges is because plants, they really can't distinguish, say, magnesium from calcium. They behave very similarly in the soil, and the plant takes both of them up in the same way. So if we end up having way too much magnesium than calcium for what the plant needs, then there's going to be a calcium deficiency in the plant. So that's why we kind of want to maintain these numbers so that the plant is getting what it needs in the proper ratios. And then finally, the last thing that I look at on the soil test report is just the nutrient levels. I find them to be kind of the least exciting, I guess. They're really straightforward. They're usually expressed in parts per million, and you get your different nutrient levels. So phosphorus, potassium, magnesium, calcium, sodium in this example. You'll also notice this column here in the waypoint report called ENR. Some labs will have this. This is your estimated nitrogen return expressed in pounds per acre. So what they're doing is telling you over the course of the growing season, you can expect roughly 78 pounds of nitrogen per acre to be released out of that soil to your crop, and 95 for the second one, 77, and so forth. Again, that's not really, I mean, it's kind of nice to know, but you can't really bank on that necessarily. That's why, you know, nitrogen has such a complex cycle. It's here one day, gone the next. So it's just really a rough estimate. And really, when we get down to it, our nitrogen rates are still calculated by yield goals. The other thing is, so these are pounds per acre or parts per million. That's how all these other nutrients are expressed. Okay. You also notice that some labs might give you a relative sort of indication of whether it's high, medium, or low. So for example, they're telling you that 16 parts per million is low, 47 parts per million is medium for phosphorus, and so on and so forth. One thing that you can do as a rough estimate is you can take parts per million and multiply that number by 2, and that just gives you a better sense as to how many pounds per acre of that nutrient is there. All right. So you can take your 47, multiply it by 2, and you can get your close to 100 pounds per acre of phosphorus in that soil. So that kind of helps people conceptualize how much phosphorus is there. The reason that calculation works, just FYI, is because when we take our soil samples are generally expressed in an acre furrow slice. An acre furrow slice means that you have a soil sample that is 6 3/4 inches deep over 1 acre. That volume of soil weighs 2 million pounds. So that's why parts per million times 2 equals pounds per acre. You might see some labs also provide a second number, and it might say something like MD equals 10, for example, in this one. What this is doing is converting the parts per million number into what we call a fertility index value. And what the fertility index value does is it basically normalizes all your nutrients into a scale from 0 to basically 100 or 150, where if you're less than 50 on that scale, that means that nutrient is deficient. And if you're above 50 on that scale, that means you're sufficient. If you're over 100, that means you're in excessive. So that all that's doing is sort of giving you a relative snapshot you can quickly look at and compare your nutrients across the board. Because, for example, 16 parts per million for phosphorus might be low, but 16 parts per million of sodium, for example, is very high, or very low, I'm sorry. So it's just a sort of a way to compare nutrients across the board. And we use FIV levels for calculating Maryland nutrient management plans as well. In the lower part of the waypoint soil test report, there's also going to be some additional nutrients presented. In this case, we have some sort of micronutrients, your sulfur, zinc, manganese, iron, copper, boron. Again, they're all going to be expressed in parts per million, just like the others were. And different labs test for there might be some variation in what they test for, and you can ask for additional nutrient testing from the labs. Say, for example, you want to know zinc, and maybe they don't offer zinc in their standard report, but you could add that into your test for a couple $dollars or something. The other one that I wanted to mention is soluble salts. You can get that. That's typically an add-on type report, but if you think you have a salt issue and that could be particularly problematic in, say, high tunnels, it might be worth doing a soluble salts test. All right, so that is sort of how to read your soil test report. My final pitch is going to be to don't guess soil test. You follow the recommendations from the lab and follow the recommendations in your Maryland Nutrient Management Plan. If you find yourself trying to figure out what you should do first, maybe your nutrient management plan is calling for lime and it's calling for fertilizer, and you might be wondering what to do first. Well, the answer is always going to be to fix your soil pH first. So if you have a soil pH that's outside of this 6 to 7 range, then it doesn't really matter how much fertilizer you throw at a field, that plant can't have access to those nutrients because they're locked up in other parts of the soil because your soil pH is either too acidic or too alkaline. Usually we're too acidic. So, for example, this chart shows nutrient availability for these different essential plant nutrients. Green means high availability, red means low availability, and this is based on your pH scale. So you can see between 6 and 7 pH, pretty much everything is available to the plant at least a medium availability. That's really good because the plants need all of these. Now, if we fall down here into, say, 5, and 5, yeah, things like copper and boron and iron are available, but things like manganese and calcium and sulfur and phosphorus and nitrogen and molybdenum, they're all strongly held to the soil and locked up in the soil, and your plants don't have access to it. So it doesn't matter in this situation, it doesn't matter if you have an excessive amount of phosphorus in your soil. It doesn't matter because the pH is off, the plants don't have access to it. So I always tell people that if you're up against the wall and you don't know what to do, always adjust your pH first, and get it in this optimum range, and then look at amending further with fertilizers and things like that. So again, for most of our crops, you want to be between 6 and 7. Now that's not for all crops. There are some specialized plants that need to be at lower pHs, blueberries for example, but for most of our crops, you're going to have to be somewhere in between 6 and 7. The other thing that I try to get people to pay attention to is their ratios between calcium and magnesium on their base saturation. So sometimes what can happen is typically high mag lime or dolomitic limestone, which is magnesium carbonate, typically that is a much cheaper limestone product than calcium carbonate. And sometimes what happens is people use magnesium carbonate over and over and over again when they lime their fields, and then all of a sudden they might have way too high of magnesium in their soils versus calcium. So I urge people to look at their base saturations and try to be somewhere in these percentages or somewhere near them to make sure you're not getting out of balance. So for example, these are all kind of within range, but say for example, one of these had a magnesium ratio up in like the 40% and calcium was down in like 20 or 30%. That would be a situation where we definitely need to lime with calcium carbonate next time and not be using high mag lime. So just be aware of that. So just to reiterate how to take a proper soil sample, doing this step properly is crucial, because if you take a bad soil sample and if you don't do it right and you submit that to the lab, yeah, they're going to run it and you're going to get data back, but you won't have a good representation of your field, and then basically all your management decisions are based off of what could be a really inaccurate data. So let me go back. I see a question about lime. So high calcium or high mag lime or dolomitic limestone is magnesium carbonate, so it has magnesium in it. And calcitic lime or high cal lime is calcium carbonate. It has calcium in it. Okay, so those are your two main liming materials. So if you are needing magnesium in your soil, then you could use your magnesium carbonate, and you could, if you need calcium, you could use calcium carbonate. So that's sort of, and you're always going to have an analysis on your limestone. It'll tell you what it is. It'll tell you your percentages, and it'll tell you if it's magnesium carbonate, or it might be a mix of both. Solucal, I'm not familiar with what it is, but again, you can look at the label on your liming material, or if you're getting it in bulk, they can supply you, the supplier can get you an analysis as to what's actually in it, so you would know if it's magnesium carbonate or calcium carbonate or some combination. All right, so to take a proper soil sample, you're going to need a couple of things. You're going to need a clean bucket, preferably a plastic bucket, not a rusty metal bucket, because that could throw your results off. You could use a tarp or a newspaper to dry your soil before you send it. You're going to need a spade or a soil probe to take the actual cores or the slices. So what you want to do is to take a representative sample, but you want it to be random, okay, of the field. You want to take different depths for different types of crops. If you're just doing turf, you can do 3 to 4 inches. Most of our field crops, you're going to be between the 6 and 8 inch depth, and if you're at fruit trees or trees, you want to be at 8 inches. Once you take your soil cores, you put those in the plastic bucket, and what you want to do is mix those really well. You want to break up all the clods, okay? So break it up really well and mix it. And when you think that you've mixed it well, mix it again. And the reason is because when the lab runs your test, they're going to use about a thimble full of soil to do your test. All right, so it's really important to have it mixed really well so that because they're only using a very, very small amount of it. You could spread it out on a tarp or newspaper to dry. One thing that I'll tell you is don't put it in the oven to dry it. I've had people suggest that, and that's not a good idea. The reason you don't want to burn off all your organic matter, so just let it air dry. And then once you have that, you just you basically take about 1 pint worth, which you put in the bag, and you send it to the lab. So again, you want to take a random sample, so you want to randomly distribute your samples across your field or whatever management area you have. You want to make sure you take enough cores to make a representative sample, and this is something that people typically don't do enough of. So usually what people do, they might take 5 out of a field or something. That's not nearly enough. What you want to do is take at least 15, preferably 20 or 25, okay? You want to make them random, but you also want to avoid areas that are not representative of the area as a whole. So for example, if this was a pasture and say the gate was right here, I wouldn't take a sample there. I would avoid that. I would take it outside of that, or say maybe there's a waterer there or a round bale feeder, something like that. I would avoid those types of areas. You also don't want to sample straight through, say, a manure pile, droppings and like that, because that's going to really throw off your nutrient analysis level. So you want to be random, but you also don't want it to be sampling areas that are abnormal from the rest of the management area. So the other thing you want to do is when you take your core, you want to discard that top layer, which is the sort of the thatch layer. Okay, so you don't want to be submitting grass, leaves, or mulch or thatch. So that gets tossed, and then the rest of it is the core that you would put into the bucket to be mixed together. All right, so there's the cores in there. You would make sure you mixed them really well, broke up all the clods, got rid of any foreign material like sticks and really large stones, things like that, and then you put it in the bag and send it to the lab. So you can send it to an approved lab. We have a list on our website, on the nutrient management website. If you send it to any one of those labs listed, they'll be doing the proper test for our region and our soil types. Really what you're looking for is a lab that does a Malic 3 extraction method. That's sort of the best one for our region. And the ones listed on our website are going to be labs that do that. How to take a soil sample. This is just showing that you would take different samples for different types of crops, if you will. So in this instance, this is a home, but you can think of them as different fields or different crops. So you would take a separate sample from the garden. You would take a separate sample, say, from the flower bed versus the front lawn and the backyard, things like that. For UMD nutrient management plans, the recommended depth for our field crops is going to be 8 inches, okay? So if you're somewhere in that 6 to 8 inches range, that's good. But the official recommendation is 8 inches. If you're just checking for soil pH in a no-till field or a pasture, then the recommendation is a 2-inch sample. And always sample consistently to get better results from your soil test. So doing all the things I mentioned, and also sampling at the same time of year, year to year. So say, for example, if you're pulling soil samples in the fall, you would want to do that every time you pull a sample, just because there can be a little bit of variability in nutrient and cycling from fall versus spring. So it's just another variable that you can eliminate if you just sample consistently time to time. Okay, that was my last slide. That's my contact information, so you can always email me or call me if you would have questions. I did put up a link for a teaching evaluation if anybody was inclined to evaluate me. And I guess I will take questions right now.
Definitely a few in the chat.
Okay, so I see one. How often would you sample a home garden or lawn? I would do it at least every 3 years. That's generally a good rule of thumb. would be every 3 years. If you're still trying to get, if it's a new area and you're, or a new lawn or things like that, and you're trying to get a handle on it, then maybe I would sample every year for maybe one or for say 2 or 3 years, and then after that you could go to 3 or 4. There's a question about the cost of a standard soil analysis. There is a slight difference typically with labs between homeowner tests and farmer tests. There's typically a little bit of a discount for farmers just generally because they're submitting so many more samples. But typically they're in the range of say $12 or $15 to $20 a sample, somewhere in there. And that would be your sort of standard. And then if you were to add on different tests, they're usually a couple of dollars here and there for, say, a different type of analysis or extraction. What do I recommend to address high sodium? So if you have high salt content in your soil, that could be difficult. Usually the recommendation is to wash it out. So the solution to pollution is dilution. Trying to flood those soils and have it leach out through the soil profile. If it is a high tunnel, expose it, so get the plastic off and let the weather, the snow and rain get on it, and try to leach it out of your soil profile. Let's see. So I see one that says they have a pasture with really high potassium base saturation, 200 to 400 parts per million, 7 to 12% base saturation. How to handle this? That is high. You so I would wonder if you have a particularly high clay content in your soil, because you can get a lot of potassium released from certain types of clays. In that situation, I mean, 7% base saturation on potassium is not terrible. It is a little bit high. As far as getting rid of it, you're basically going to be growing a crop, and hopefully, if it's a pasture, try to be removing it via having the animals graze, and also if you can make hay off of it over time, you can maybe bring that down a little bit. Let's see. A recommendation for high organic matter. So if your organic matter is too high, well, one thing that you can do to get rid of organic matter is tillage. Every time you aerate the soil, you're going to activate microbes, and when they get aerated and active, they're going to chew on your organic matter, and you can burn off organic matter through tillage over time. But generally speaking, having too much organic matter is not generally the problem. Usually it's the other way around. Let's see. Does it make sense to have high magnesium but low base saturation? It could, yeah, it could happen if your other base saturation numbers are off or occupied by other things like, say, calcium or potassium or hydrogen or sodium. So that could be a source. And also, if you have a low CEC to begin with, that can be sometimes throw off those ideal numbers just because you have a low CEC to start with. All right, did I miss any? I don't see any other ones.
Yeah, I think you got great questions, everyone. So thank you very much.
Yes, thank you all very much for taking your lunch hour with us.
Absolutely. I'm going to stop recording at this point.